The other type of a problem we will solve here now, problem on this tapered cross section bar element. By using elimination method we will solve the problem. He has not mentioned anywhere which type of boundary condition we are handling here. If they have not mentioned, we will take directly elimination method. If they have mentioned which mentioned type of handling boundary condition is given, same boundary condition we need to take. Here I'll read the problem. Determine the nodal displacement stress in each element and reaction at fixed support for a thin plate of a uniform thickness of 1 mm shown in figure below. We need to determine the nodal displacement stress in each element and reaction at the fixed support for a thin plate of a uniform 1 mm thickness, right, is shown in figure here. Thickness is equals to 1 mm. This is a tapered cross sectional bar element what we have here. And then Young's modulus of this element has used to make the bar element. The material is steel 200 gigapascal. Weight density of the plate rho is equals to, that is a 76.6 into 10 to the power of minus 3 Newton per millimeter cube. In addition to its weight, it is subjected to a point load 100 Newton at the midpoint. At the midpoint, the element is subjected to a point load. The model, the plate with a 2 bar element. We are converting this single element into a 2 elements. This taper bar element is not possible to represent as a line element. You can see this one, the line element. Is it possible to vary the dimensions of this line element from this corner to this? But in a two-dimensional diagram we can easily represent, but one dimension it is impossible to represent. First, what we need to do, we need to bring this varying cross section in terms of a uniform cross sectional element. So instead of taking a single bar element, we need to convert in terms of a 2 bar elements. We need to consider a axis with respect to this point, and element number 1 left hand side with respect to this axis, on the right hand side I will take a element number 2. Means I need to find the mean value of this given bar element by using these two values. Left hand side width is given 60 millimeter, right hand side width is given 30 millimeter. I'll take capital D is equals to 60 millimeter and small d which is equals to 30 millimeter. So what is the mean value of this one? D mean, which is equals to D plus small d divided by 2. Means we'll get this 2 value, add divided by 2, we'll get a 90 divided by 2 is equals to 45 millimeter, that D mean, right? So after getting that mean value of D mean, we can get easily this element number 2 value and element number 1 value. So we need to convert this tapered cross section in terms of a uniform cross sectional element. Then it is possible to represent in terms of a one dimensional FE model. Clear? So now first task is what we need to find out the area of cross section. See, in this given problem he has given the dimensions width and thickness and length of the element is given. The length of the element is equals to how much? 240 millimeter. Total length of the element, half of the element is equals to what? L divided by 2, that is equals to 240 divided by 2 is equals to 120 mm at each element we need to consider due to the given dimensions, right? So all the characteristics I have explained here. Just I will copy that all the characteristics what we need to find here: displacement, stress and reaction force. These three things. Just I will write the given data here. So capital D 60, small d 30, T thickness is given 1 millimeter and length of the bar element 240 millimeter. The half element we are considering as element number 1, another half element is considering as element number 2. L1 is equals to L2 is equals to L by 2, 120 millimeter with respect to the mid axis. Load has been applied at the midpoint of the bar element, that is 100 Newton at the mid, and then Young's modulus E is equals to 200 gigapascal is equals to 2 into 10 to the power of 5 megapascal. Density of the element is given here that is a 76.6 into 10 to the power of minus 3 Newton. We have a Newton per millimeter cube. We have a self weight. So due to the density, there will be a force at a element is F1, F2 and F3. Each node that is equals to this equation we will take to find the self weight load which is exerting on a member on this element. Apart from that self weight, we are considering the load has been applied, that is at the mid node. Two types of forces are there. We need to add the both forces, then we'll get the global force vector. What is that global force vector? Global force vector which is equals to small f global force vector. I have taken capital F applied force plus of force due to density self weight of a bar element, that we need to find out. So we got the idea. First we need to convert this taper bar element in terms of two elements as a uniform cross sectional element. Then same procedure we need to adopt to find out the elemental stiffness matrix, global stiffness matrix, global displacement vector. Till that global displacement vector it is remains same. After that global displacement vector, the two types of forces are there. Like in a thermal problems we have solved thermal load and a normal force is applied on a bar element. Similarly, normal force with the self weight, both the forces we need to add, then we will get a global force vector. Normally what we will consider, applied load is there at node number 1, node number 2, node number 3. That node we have taken, if it is a fixed is 0. Applied load, what given load we have taken F2 and F3, and we have solved the problem based on the boundary condition, eliminating the rows and column by using elimination method. Then we'll get a displacement at the free end with the force. So now similarly here we have a addition to that force as a density self weight. Due to the self weight, what will happen to the element, right? So first task, we need to convert that given tapered cross sectional element in terms of a stepped bar element, which I have drawn here. This left hand side portion I have taken with respect to the mid axis largest element, and right hand side I will taken as a smallest element when I represent this is a tapered element, right? So just I have converted this tapered element in terms of a stepped bar element to draw a finite element model clearly. We need to convert that. I'll consider this element number 1. Now tapered bar is converting into a stepped bar, correlating the volumes. By correlating the volumes, I'll draw a tapered cross sectional element, an equivalent element of a bar element rectangular shape I have drawn here. He has given a largest width d. I have considered 60 mm, and then mean value we have found here, that is equals to 45 millimeter. After getting that both the values and length of the element L1 from this point to the next point here, length will remain same and width is not remain same. W1 is equals to question mark, which we need to find in a given problem. We know that is equals to 1 millimeter. Why? To find out the area of cross section A1 for this element. We are doing this process. Consider a volume of a tapered cross section. I have considered a volume of a uniform cross sectional element. See here. So volume means V is equals to area into length. A1 is equals to, for this tapered cross sectional element, W into T. What is this W? D plus D mean both the width divided by 2 into T. So that I have taken here D plus D mean divided by 2, and then into T, that is area of cross section, and into L1. Similarly, area of cross section number 1 for a element, a uniform cross sectional element considered, so that is equals to W1 into T. So when we will multiply this length, it becomes a volume. So we know that a length L1 both are remain same, and thickness of the elements is remain same here. So I have taken here, you can check out the thickness of the both elements is equal, length is equal, but this width is not equal. So which we need to find question mark. To find that, we have this E is equals to 1 mm, L is equals to 120 mm, L1T will get cancelled, remains W1D plus dm divided by 2. just width plus mean width of the given bar element is equals to 60 plus 45. 60 plus 45, this is a 45 we have found at the mid here. 60 plus 45 divided by 2, that is a 52.5 millimeter. Then we want a area of cross section. To find out the stiffness matrix, what is the stiffness matrix? K is equals to AE divided by L into 1 minus 1 minus 1 1. So we want this area of cross section after converting this tapered in terms of a rectangular element. How we'll find that area again? So W1 into T, 52.5 mm into 1, that is equals to 52.5 mm square. So area of cross section for this element we found. Similarly we need to find the area of cross section for this element and W2. So I have considered a element number 2 here, a tapered cross sectional element. It will get start from this mean portion to the smallest dimension, mean to the smallest dimension, uniform cross sectional element. Mean value of this bar element with respect to width is equals to 45 mm, smallest is 30 mm. Length will remain same from 240 divided by 2 is equals to 120 L2. This is also remain same, only W2 is unknown, so we know that thickness. So we know that the volume of the rectangular element, volume of the tapered element, that is equals to A into L2, A into L2, mean dm plus d divided by 2 into T, area of cross section of this tapered element, into L2, volume of this taper element, U2 into T, area of cross section for this element, and L2 is multiplied to this area of cross section volume we got. We know that length are remain same, thickness is remain same, then W2 is equals to dm plus d divided by 2. 45 plus 30 divided by 2 is equals to 37.5 mm. The area of cross section for this element, which is equals to A2, is equals to W2 into T. So what is the W2 we found here? The A2 is equals to W2 into T. 37.5 into 1 is equals to 37.5 mm square. So now the next step of elemental stiffness matrix we need to find. Before going to find, we need to represent this a FE model, converted this tapered cross section in terms of a stepped bar element. We have how many nodes after converting that? A two nodes here at the element number 1, at the element number 2 another node. So we have I'll represent this is a node number 1, node number 2 and node number 3. So 3 nodes are there after converting that one tapered cross sectional element in terms of a two stepped bar element. Has a 2 area of cross section and 3 nodes. Each node has a 1 degrees of freedom and force has been applied at the mid node, and first node is fixed, last node is free. But we have a self weight at all the nodes. In all nodes we have a self weight. See, we have here a global force F1, F2 and F3 at node number 1, node number 2, node number 3. Displacement will occur at node number 1 Q1, displacement will occur at node number 2 Q2, displacement occurs at node number 3 Q3. Length of the element 1 L1, length of the element 2 L2 we have represented. For this model is satisfy only for a stepped bar element. This FE model is representing for a stepped bar element, not for a tapered cross section. And why means we cannot be represent the varying cross section in a line element. Uniform it's there, then it is possible to consider a one dimensional element, right? So that is the reason we need to convert from tapered to the stepped bar uniform cross sectional element. Due to the analysis what we are carrying is a finite element analysis by using one dimensional characteristics of the given problem, right? We have a elemental stiffness matrix, step number 2 of a finite element method. We need to find the stiffness matrix for element number 1, stiffness matrix for element number 2. We know that KE AE divided by LE 1 minus 1 minus 1 1. This equation, how many elements we have? Only 2 elements. Consider element number 1, E is equals to 1, then K is equals to A1 E1 divided by L1. We found that area of cross section for a first element which is equals to 52.5 millimeter square, and Young's modulus is common for both elements, 2 into 10 to the power of 5 megapascal. Length of the element for both elements are common. This remains same. Calculate this value. We got that 0.875 into 10 to the power of 5, 1 minus 1 minus 1 1. Then I'll take a 10 to the power of 5 common here. This value I'll multiply inside the matrix. We'll get a 0.875 minus 0.875 minus 0.875 plus 0.875. Now we need to represent the row name and column name which we have here. The element is lies between the two nodes, start from node number 1 and ends at node number 2, that element number 1. So the case stiffness matrix for element number 1, what we have, the characteristics of row 1 and column 1 with respect to the node 1, we have given 1 and 1. So the characteristics of a node 2, the matrix is second row, second column, we have given second row, second column name as a 2 2 for a element number 1. Similarly, we will find the elemental stiffness matrix for element number 2. E is equals to 2. We have K2 is equals to A2 E2 divided by L2, 1 minus 1 minus 1 1. So A2 value we have found here, that A2 value substitute and Young's modulus and length of the element are remain same, 37.5 into 2 into 10 to the power of 5, 20 length, minus 1 minus 1 minus 1 1. Calculate this value, which is equals to 0.625 into 10 to the power of 5, 1 minus 1 minus 1 1. So I'll take 20 to the power of 5 common. This value I'll multiply inside the matrix. We'll get this matrix 0.625 minus 0.625 minus 0.625 plus 0.625. Now this elemental stiffness matrix for element number 2 that start from node number 2 and ends at node number 3. The characteristics of a node number 2 is first row, first column. The characteristics of a node number 3, second row, second column. That is the reason I have given a first row, first column name as a 2, and 2 for second row, second column name I has given as a 3 and 3 based on the characteristics of the element. Fourth step of finite element method is in a global stiffness matrix. We know that we have both the K1 and K2. Add both the values, will get a global stiffness matrix. We have 3 nodes, and 1 degrees of freedom, that is equals to 3 into 1, which is equals to 3. We'll get a 3 cross 3 matrix. 3 cross 3 matrix. We know that now we need to take a 3 cross 3 matrix here. As usually, you know that find the first row where it is exactly here, and we don't have any first row, first column value, that is this one, first row, first column 0.875. First row, second column is here, so minus 0.875, but first row, third column we don't have, that is equals to 0. Similarly, I'll go with the next second row, first column, second row, second column, second row, third column. All these values will get now. Second row I'll find in the first matrix, and in the second matrix also we have second row, first column. We'll see here, this is the value, second row, first column, minus 0.875. Second row, second column, we have this one, 0.875, but we don't have here first column, but to get start from 2, we have a 2 values, right? Second row, second column, 2 values, we have 0.875 plus 0.625. Add this one, will get that values, these 2 values, add it, we have this second row, second column value. Then second row, third column value we need to get, but here we don't have any third row, second row, third column, but here we have the second row, third column value, minus 0.625. Then we'll go with the third row, first column, third row, second column, third row, third column. All these values will get. Now we'll check out in a first matrix, there is no third row, we'll get start from 1 and end at 2. We'll read this one, there is no values with the third row will get start here in this matrix. So we have third row, first column, we don't have any value, that is equals to 0. Third row, second column, we have this value, minus 0.625. Third row, third column value, we have this one, 0.625. So we have taken this, I have taken a very fast. Why means I have solved so many problems. If you wanted to get the idea about this one in a matrix assembly, derivation is also I have given for a tapered bar element. Go through that videos and you will get the clear idea again if you have any doubts. The global stiffness matrix, we have only this will be get changed 1.5, rest of the remaining values will remain same. This value addition. So after adding that, we'll have a global stiffness matrix. Now we need to get a global displacement vector. We have a 3 nodes. Each node has a single degrees of freedom q1, q2 and q3. At node number 1, node number 2, node number 3, displacement vector becomes q1, q2, q3. So then after this we need to find out the global force vector. How we need to find out the global force vector? We have two forces from figure. Two types of loads. One is a force due to a self weight, that is a density is considered, and also force is applied at the mid of the bar element, that is 100 Newton. F1 is equals to 0, F2 is equals to 100 Newton, and F3 is equals to 0. Capital F1, F2, F3 I have taken as a force which is exerting due to the application on a element. Small f1, small f2, f3 I have taken as a density load. So we need to find out the global force vector small f. We have this one. We know this f1, f2 and f3 value from figure. Then we need to find out the small f1, f2, f3 value due to a self weight. How we need to find out? We know the equation. All of you remember this equation. Density rho e is equals to AELE divided by 2 into rho into 1 1. So this equation is very much important. Remember it. F1, F2, F3, small f1, f2, f3. Node number 1 force due to self weight. Force due to self weight at node number 2. Force due to self weight at node number 3. Actually I have written 2. Now make it the correction here. 3. This one is 3. F1, F1, F2, F3. Make it the correction of this one. So now after finding that, consider a element number 1. We have this equation. Rho 1 is equals to A1 L1 rho divided by 2 1 1. Rho 1 means small f1 f2 value for a element number 1. So we have these values. So now we need to substitute the value of A1 we have found 52.5, and length of the element 120 mm, and density of the element is 76.6 into 10 to the power of 6 is given, divided by 2. 1 we need to take common. Then the rho is equals to this value calculated. When we'll calculate, that value is equals to 0.2419. that value I have multiplied inside this matrix. Then this total value becomes, in terms of a vector, 0.2419. This is at node number 1 and this is at node number 2. F1, small f2 I have taken. So we have found a self weight force on a node number 1 and node number 2 in a element number 1. And then we need to find out a element number 2 self weight, that rho 2 is equals to A2 L2 rho divided by 2. Rho I have taken common. Density is common for both elements. Why? It is the same made up of material. So 37.5 120 divided by 2 76.6 into 10 to the power of minus 6 1 1. Only this value has been got changed now. So then after calculating this value, we have this value is equals to 0.172355. This value, when I'll multiply inside this matrix, that matrix is yields to a vector we have for a force 2 and force 3. Y element will get start from node number 2 and ends at node number 3, the element number 2, right? So then we'll say it's self weight force at node number 2 F2, at node number 3 F3. We have two forces here we can see. So now we'll get the global self weight vector or global force vector due to self weight. So we have a global self weight vector. Density is equals to density 1 plus density 2, which is equals to, we have these forces, add that have F1 F2 and F3. So this value directly will take F1 F2 and 2. We have two values. We have no element will get start from 1 to 2. It will get ends. When this element 1 is ends, from the same node element number 2 will be get started and ends at node number 3. The effect of forces what is occurring in a node number 2 based on the element number 1 and element number 2, that effect we are adding here. So 0.249 plus 0.17235 at node number 2 only. So this element number 1 effect is not occurring at the node number 3. This element number 2 is not occurring at the node number 1. So why, where it will get affected? Only at the node number 2, right? So only that value will get added. So 2 value, right? So then last force value is remains same. F1, small f1, small f2, small f3. It is a self weight due to the consideration of density of the bar element. Now we got the global self weight vector for a given problem. After getting the global force vector due to self weight, this one, then we'll find out the global applied force at each node. We know that at each node we have a force in a given problem. Here a force F1, F2 and F3. F1 is equals to 0, F2 is equals to 100 Newton, F3 is equals to 0. That applied force in a member F1, F2, F3, F1 is equals to 0, F2 is equals to 100, F3 is equals to 0 Newton. Then we'll find the global force vector is equals to F small f is equals to capital F plus rho. So this is a self weight, and this one is applied force. So the self weight force we have found here, just you move it, copy the same, and then this is a global force vector. Add both values. 0 plus 0.249 is equals to 0.249 total force at node number 1. So then 100 plus 0.4125 is equals to 100.41425. Then 0 plus this value, that 0 plus 0.17235 is equals to 0.17235 at node number 3. Fourth step, equilibrium equation. KQ is equals to force. We are very well known. All the values substitute here. We have substituted. Then we'll apply the boundary condition. Fifth step. After equilibrium equation, applying the boundary condition, Q1 is equals to 0 due to fixed R1 and C1 are eliminated, but node number 2 and 3 free and forced. Node number 3 is only forced due to self weight. It should not be eliminated. So then 3 cross 3 matrix becomes 2 cross 2 matrix. After removing first row, first column, this remains same. So that will be copied here. So we have here the 3 cross 3 matrix becomes 2 cross 2 matrix here. Now use the calculator. All this coefficient, enter it in your calculator as a, this one is a A1 value, B1 value, C1 value, A2 value, B2 value, C2 value, and press equals button. You will get a X and Y. X is equals to Q2, you will get Y is equals to Q3 unknown. You will get by using the equation. No need to represent to reduce the time in your external examination. This like this you wanted to do. The nodal displacement vector, now we got that is equals to Q1 is equals to 0, Q2 is equals to 1.638 into 10 to the power of minus 3, Q3 is equals to 1.2666 into 10 to the power of minus 3 mm. So now after that we need to find out the stress in each element. I have used that equation directly, generalized equation. Sigma is equals to E divided by LE minus 1 QI plus 1. We have two elements, element number 1 and 2. We have element number 1 initial node 1, element number 2 initial node 2. So I'll take E is equals to 1, I is equals to 1. We have that stress is equals to 1.915 megapascal for element number 1. When I'll take E is equals to 2, I is equals to 2, the stress in a member element number 2, that is equals to 0.005 megapascals. Then we have a reaction force in a given element R is equals to KQ minus F. This equation is used to find out the reaction force at node number 1, at node number 2 and node number 3. K value we know that I have written here. Q value just now we have found this value. So that value will get here, this value we need to substitute. We'll get a reaction force. We know that force, global force we have found in the given problem. This value we need to substitute here. After that, resolving this, we know how to resolve this matrix. You check out in a previous video, each and every step I have given, how to get a this 3 cross 3 matrix, multiply with the 3 cross 1 matrix, will get a 3 cross 1, then we'll subtract these values with this, and then we'll get this answer at node number 2 and node number 3 is equals to 0. At node number 1, minus 100.568 Newton. Similarly, same problem, just element has represented vertically, that's all. Vertical bar element. Step has only this step will get changed, rest of the problem is remains same. Only the FE model will get changed, elemental stiffness matrix, global stiffness matrix, global force vector. In that density we are considering, due to density self weight forces we have, and also we have a normal force applied forces. Combination of that will get a global global force vector. After global force vector we'll make equilibrium equation, then we'll apply the boundary condition, remain same. Each and every step is remain same except FE model. Bar is vertically placed, that's all. This is a take as an assignment, all of you solve the problem. In next class, in next video, I'll take a penalty method or type of handling boundary condition. Thank you one and all.